So last week we covered the normal distribution, and this week we're going to cover sampling distributions. So we have sampling distributions. Which is chapter 5, and then we'll also cover confidence intervals in chapter 6. All right. So I think the very first week of class, I said we study statistics because it allows us to make conclusions from limited data. And I said we have this thing called a population, which is too large for us to study or observe. Or it's too large for us to study directly. And so instead of studying the population, we take a chunk out of it, a randomly selected chunk, called a sample. And we study the sample. That's what we do. And based on what we see in the sample, we want to make conclusions about the population. And we know that if we were to take another sample, it's not going to look exactly the same as the first sample we took, but yet either sample should be equally valid towards making conclusions about the population if we selected them in the same way, right? So if both of these samples are representative of the population, they would both be equally valid for us to. It would be equally valid for us to use either sample to make conclusions about the population. And so everything here, and pretty much for the rest of the course, we're putting an assumption that the sample that we're selecting is selected randomly. Okay, so we assume simple random sampling. And sometimes this is a dangerous assumption to make. Okay, all of the math and the theory that the tests we learn make this assumption of simple random sampling. And so when you do I don't know, research or things in the I guess in the quote real world, if this condition or assumption is violated, you might run into some problems. Or at least to some degree, you're assuming, maybe you're dealing with, patients of, who have diabetes. Obviously, that's not going to be representative of the entire population, but maybe to some degree, you're assuming that your group of patients with diabetes is representative of the general population of people with diabetes. Maybe that is a good or bad assumption to make. So a lot of times you'll hear about these research findings, and they'll have based on a sample of 70 patients or something. You have to ask, well, how representative are these 70 patients of the general population of which they're making conclusions about? Okay, if it's representative, then you're good. If it's not representative, then maybe we run into problems. Okay, so anyway, we're going back to sampling distributions. The idea here is let's say I take a sample, okay, from the population, and from this sample, I observe the mean of the sample, okay? And I get the sample mean y bar for that sample, okay? let's say I throw that back into the population. I mix up the population, somebody else takes another sample, same size, okay? So if this is a sample of size n, and it has sample mean y bar, let's say I do that again, okay? I take another sample n, and I get another y bar, okay? This y bar is probably not going to be the exact same as this y bar, okay? If I took 100 random people, and I got the average weight, you know, maybe it's 163 pounds. Maybe I put those, I say thank you very much. I go back to the population, somehow I select another 100 random people, okay? Take the average weight. Maybe it's something else. Maybe it's 155 pounds, or 170, or 180, whatever it is, okay? Maybe, you know, there might be, well, with 100 people, it's probably not going to vary that much, but the sample mean is going to be different from sample to sample, okay? Let's say I do this over and over again. Take another sample, get another sample mean y bar. Okay. What is the distribution of y bar? That's what we want to know. Okay? That is essentially what a sampling distribution is. The distribution of y bar is our sampling distribution. Okay? This is our so if the population, okay, we've got a population, and if I just repeatedly take different samples, okay, different random samples from the population, and I do this over and over and over again, each time I take a random sample, I get a y bar, and I keep track of all the different y bars, all the different sample means. What is that distribution going to look like? Okay, well, maybe we can explore this doing a simulation, okay, with the computer. You can always, if you hate this, we don't have to do it, but I'm going to try, okay. So I'm going to fire up R again. We're going to have a population. Let's see. There's a question. Yes?
Yeah, when we're talking about random variables, isn't this kind of the same if you take a sample, let's say 50, if the probability of success is, I'm sorry, binomial distribution. If the probability of success is 0.6, let's say, we repeatedly take a sample of a certain size, that will approach being 6, right? Or,
it's very similar, okay, and in fact, it is the same concept, but what we're going to see here is that the population has we're looking at a numeric variable in our case, okay, and in the example you're talking about, the population, it's technically categorical, success and failure, okay, and maybe there's a 70% chance of finding a success in the population. But yes, they are highly related, and actually that's why the book puts in the normal approximation to the binomial in this chapter 5. We'll visit that later, okay? We'll visit that later. Okay, so let's take a look here. I'm going to create a population here. All right, so let me just clear out everything here. Is my thing working? Oh, okay, I had the wrong window. All right, so let me just, okay, so I'm going to create something called the population. And what I'm going to do is I'm going to have R just simulate some random values here. Okay, so there's a function called rnorm, and that basically generates random numbers. So if I could say, give me 10 random numbers coming from the normal distribution with a mean 100 and standard deviation 15. So this would be like IQ scores, okay? To make it easier to digest, I'm going to have it round these numbers. What just happened? So these numbers are different from the other numbers because every time I ask for our norm, it generates a new set of numbers here. Okay. All right, so I'm going to ask R, and actually, if you want to repeat this at home, I'm going to just do a set seed so that our random number generations will be identical. Okay. Excuse me. I've got a tickle in my throat. And it's killing me. So I'm going to create something called a population. And this will have I need to get like a water here, so excuse me. I'll do 10 to the 5 people, mean of 100, standard deviation 15, excuse me. I'm going to just excuse myself. Sorry. Get a glass of water. I apologize.